All right, Mr. P helps with calculus. This is Unit 1, Day 9. So now we're going to be doing 3-point continuity tests to determine if a function is continuous at any given point. And yes, the way I'm showing you today is the way that they are going to expect you on AP board on the exam itself. All right, so the first thing we have here is a question about determining limits. Once again, I'm going to let you go through that yourself. Honestly, that has actually been covered in a prior lesson. Our 3-point continuity test. There are 3 things that occur for a point to be, and it really just makes sense, for a point to be continuous, or a function to be continuous at a given point is the way I should say. So what it's saying is that if x equals c, so at some given number, it could be anything. So in this case, it just happens to be c. This point right here is at c, comma, f of c, just meaning an x and a y. Well, it says that f of c has to be defined. That means it must exist. In other words, it can't be a whole. There has to be an answer for f of c. F of c has to have an answer. That's all it's saying. So it can't be a whole. It's got to have an answer. And number 2, it states that f of x's limit has to exist at c, meaning the left and the right hand sides have to meet somewhere. They have to meet somewhere. Well, technically they don't have to meet right here. They could meet anywhere. So in other words, what I'm saying is that this right here, this f of c does not exist. It would be a whole. Here, f of c does exist. There is a point. There is a value at c. There is a height. And there is a limit. The limit is below it, but it does exist. So far, this one up here did not meet the first criteria. This one down here meets the first criteria because of this point. It meets the second criteria because this left and right hand sides do approach the same height. So far, so good. But when it falls short is number 3. This point has to be the same answer as the limit. Whatever the limit was has to be the same as the value. Well, that just makes sense if you look at this example right here. Yes, it does approach the same height. So yes, a limit does exist. That's number 2. This point does also exist. Yes, f of c is defined. That's what that means. And then they have to be the same. And that's what continuous means. It means that you could basically draw this function in one continuous motion without picking up your pencil. That's technically the definition of continuous. It means it never breaks, never ends. It's all one continuous motion. Now, it just kind of makes sense. And yes, like I said a second ago, yes, you must on the AP exam show it with this 3-point continuity test. And I would even suggest putting 1, 2, and 3 and just get used to doing it that way. So yes, 1, figure out does f of 1 exist? So this is a piecewise function. So they're telling us that the function is absolute value of x anytime x is less than or equal to 1. And they're telling us that the function is 2x plus 3 anytime x is greater than 1. So there's 2 different pieces. Now I've already graphed the pieces. You can see this is the absolute value piece, and this is the linear piece of 2x plus 3. And we're supposed to find out whether or not it's continuous at 1. Now, I know it's pretty obvious since I've already drawn the graph. Yeah, clearly you can't draw this piece and then jump over to here without picking up your pencil. So, yeah, I already know the answer is going to be no. But on the test, you can't just write no. You have to prove it using the 3-point continuity. Does f of 1 exist? Yes, it's right here. F of 1 is 1. Does the limit exist? Do the left and right hand sides at 1 meet at the same place? No. Clearly there's a jump discontinuity, and we'll get more into that later on when we talk about ways that functions can be discontinuous. But for right now, clearly the left and the right hand sides are approaching 2 different heights. And then step number 3. Is the limit the same? Well, d and e cannot be the same as a number. So d and e and 1 are not the same. So we just say that f of 1 does not equal. There's lots of ways you could write this, as long as you're writing it in a way that makes sense. All right, so I look at example number 2. 2 new functions, both linear pieces. Now, clearly you can see I've already drawn it. We're supposed to figure out if f of x is continuous at x equals 1. Well, I start with finding, does f of 1 exist? Well, this is a greater than sign. This is a less than sign. Neither one of them say that they can equal 1. So no, there's a whole at 1. So this first rule does not work out because it does not exist. It is not, f of 1 is not defined. This is what you could write, to be honest, or it does not exist. Does the limit exist? Yes, it does. The limit exists at 3. Both the left and right hand sides are both approaching a height of 3. And obviously, d and e cannot equal 3, so these two are not the same thing. All three of the 3-point continuity tests must be true in order for the answer to be yes, continuous. These both examples have been no. They are not continuous at that point. They are continuous at other places, just not at the point they're asking us. This is our rational function, 1 over x minus 3. Yes, we know there's a vertical asymptote, but that doesn't mean it's not continuous at 3. Well, let's look a little bit deeper. Well, I can clearly see that the vertical asymptote is at 3, but so let's use our 3-point continuity test to prove that, yes, it is not continuous. I know I shouldn't have worded it that way. No, it is not continuous. Does f of 3 exist? No, it's a vertical asymptote. Does not exist. Does the limit exist at D and E? No, because they are not the same. Now, I know what I said earlier, and number 3 technically is true because they're both D and E. So technically, these are, I guess, both are the same, although I don't even like saying that either. But no, this is not continuous at x equals 3 because all 3 of these had to be the same. Now, whether or not you consider this one to be true or not, I think kind of goes down to the way you think of does not exist. I don't really think does not exist is a real thing. So I don't even like saying this is true. This is really not true because does not exist cannot really equal does not exist. Just because it doesn't exist doesn't mean it's the same as another one. All right, let's look over this one, example number 4. Does f of 2, is it clearly defined? We're trying to figure out if it's 2 is defined. Well, it's not in this piece. It is in this piece, and it's not in this piece. So x equals 2 has to be this piece, and it has to be 5. So there's our answer right there. Does the limit exist? Well, I've taken the opportunity to already graph it. I used tables in order to be able to graph it. Clearly, you can see, yes, both pieces do meet at that same height of -7. And then the third point when it comes to continuity is that the limit has to be equal to the same as this point. In other words, could I draw this function without picking up my pencil? No. I would get to this point right here where the hole is, and I would have to pick up my pencil to put this point all the way up here. Even though it's defined, it's not equal to the limit. So therefore, this point is not continuous. I know, it seems like such an easy concept that I'm making more difficult, but the point of the 3-point continuity test is that it's always going to work. It's always going to either prove or disprove the fact that it's continuous at that point. And that's really a lot of what we do in this class, is about proving why something is what it is. All right, a couple more examples. Number 5. So once again, we have a piecewise function. Anytime x is less than 1, we use this. And we use the exponential when it's greater than or equal to 1. Now, it's kind of hard to draw that, but that's my exponential piece. I did the best I can to make it as realistic as possible. The other one was linear. Does f of 1 exist? Yes, it happens to be 5. Does the limit exist? Do these two pieces meet up together? Yes, they do. They both have a height of 5. Are they equal to each other? Yes. This is continuous. This function f of x is continuous at x equals 1. All right, this one over here. Is it continuous at x equals 0? Does x equals 0, f of 0 exist? Yes. It's all the way up here at 3. Does the limit exist? No. Clearly, these two pieces on the left and the right-hand sides are approaching 2 different heights. The one on the left is approaching a height of 1. The one on the right is approaching a height of -2. They're not the same. And I could have done that just by plugging the numbers into the two equations as I did up here. They're clearly not the same. Even if I didn't have the graph, I could have proved it up here algebraically. And therefore, 3 is not the same as D and E, so therefore the third one is not true either. So this was true. Number 1 worked, but the second and third one did not. So therefore, x is not continuous. I didn't write that answer up there, but yeah, it's not continuous. The answer is no. All right, hope this helps with how to use the 3-point continuity test to determine if a function is continuous at any given value. Thanks again for watching, and I'll see you in the next video.